Okay, so if you have not watched the previous chapter itself, your current of electricity, stop here and go and watch the videos itself, because this is an expanded part of your current of electricity. Is the follow-up chapter based off that. So you haven't watched the first video, the current of electricity videos, you might not be able to understand what's going on. Okay, so basically this table that you see down here is just an expanded list of all the different symbols that you might encounter in your secondary school. Okay, now if you notice over here, if you are using from the socket or basically a power source that is not a battery, we basically just draw them in this case. So a direct current itself will move from plus to minus. Okay, and for your alternating current itself, because of the word alternating, basically the direction of your current keeps changing. Okay, so same thing, conventional current flow and electron flow itself. If you see the word electron, you start from negative. By this, the default conventional, we will just start from positive to negative. Okay, then this is your cell. Cell, the longer side is your plus, the shorter side is your minus itself. Okay, so your battery, even though we say battery very often, it is for your group of cells. Okay, so you have a switch, open switch and a closed switch, and this is what we call a two-way switch. And a two-way switch is a little bit special. So basically, if you have, for some of the students, if you all live in private houses like a semi-detached or whatsoever with many stories, right? So like 3 stories, 4 stories, and so on and so forth. Some, especially at night, just when you're about to sleep, right? You're just sleep on your bedroom that is like 3 stories high. Okay, then the problem is the living room light downstairs is not off. So what do? We will just use a two-way switch. So at the corridor or at the staircase itself, there might be a switch to actually be able to control the lights downstairs. So because of this, you can use a two-way switch. So you can just notice that, for example, this part is downstairs. This is level 1. Okay, so this is like your first floor, level 1. Okay, then you have this part. Maybe this one is at level 3. So if you want to just turn off the lights, you don't need to go all the way down to level 1, turn off the light, and then you run up to your level 3 because you're scared of the dark. Okay, so because of this two-way switch itself, some hotels or suites or even like those private houses, you will actually have this one. So for my students who, like me, who live in flats, we don't usually have two-way switches because there's no point. Because you don't need to travel a long distance or you don't need to climb up and down stairs just to be able to turn off your lights and fans. Okay, next one is your variable resistor over here. It's your rheostat. Okay, then you have this special term called your variable potential divider. This one will actually be a subtopic by itself. So at the next few videos itself, I'll introduce to you what is a variable potential divider or what we call a potentiometer itself. Then your fuse. Now this one, we will only learn about your fuse in your next chapter on practical electricity. So you can see the difference between your fuse and your fixed resistor. A fuse have this line in between. So that is why normally when we draw a fixed resistor, I always remind you all, don't draw a line in between the rectangle itself because that actually represents a fuse. They are two very different things. Okay. For your bell, you don't really need to know how to draw it. Just know that it exists and what it looks like. You have your LDR and your thermistor. Now, these two are basically what we call your transducer. Okay, but you don't need to know this one. Basically, you don't need to know the term itself. But if you do, if your school does mention it itself, do take note what they are. Okay, transducers. Then your semiconductor diode itself, basically this one, remember, it does not obey Ohm's law. Okay, it doesn't obey Ohm's law. You don't need the circle outside. The circle is just some symbols itself. Some schools will need you to draw a circle, some schools don't. Go and double check your school notes. But typically, we don't need the circle itself. Okay? Then for your wires itself, if you notice this, right? This usually tell you is parallel. Okay? So if you want to draw wires, but the problem is there's not enough space and it might overlap. So what you want to do is you want to show that your wires, you will basically, I have a straight wire, this wire will jump over it. It's not touching it, it's not connected. Okay, but this one are quite rare, so not all the time you have this. Same thing for your earth and ground. So if you have done your static electricity, this is the symbol for grounding or earthing itself. This one we also learn it in your next chapter on practical. Coil of wires and transformers, we only learn this in your second last chapter. Okay, so which is still some time later. So first things first, let's talk about your series and parallel circuits first. So what exactly is a series circuit? So a series circuit is all your components are connected in a single loop, which means if I were to take my finger and I start from the plus, without lifting my finger, I can actually draw one single loop. One loop. So this is a series circuit. Okay? So there's only one pathway. So what's so special about your series circuit is current is the same at any point. So if I take current here, let's say this is 2 amperes. I take current here, it's also 2 amperes. I take current here, everything is 2 amperes. Because remember when I was teaching you about your current electricity in the first place, I told you guys that as long as you have a single loop, this is a constant flow of electric charges itself, or basically your electric current is constant. So as long as one single loop, at any point, it will always be same current. Okay? So all your emitters here will have the same reading itself. Now, for your potential difference, your voltage, right? Just remember your EMF is the sum of your V1 and V2. Okay? So total V is V1 plus V2. All good? Then for your effective resistance itself, so basically if you just imagine yourself, if you are the electron or your electric charges when you are traveling through, how many obstacles do you face? You face these two obstacles, right? So all you need to do is add them up. So if you add these two up, right, this is your total R. Or sometimes we call this your effective R. Okay, they mean the same thing itself, is R1 plus R2. So sometimes we can actually just simplify the two. 1 plus 2 is 3. We can just draw these two together, combine it, and treat it as it's just a 3 ohms. Okay? So when you have a series circuit, first thing, always ask yourself, number one, what is your circuit? Is it series or is it parallel itself? So first thing, for series, number one, we always use V equals I times R first. Okay? Remember your last chapter? V equals I times R first. So number one. Then number two, because this is series, ask yourself now, total I is I1, is I2. They're all the same. Okay? Number three, total V is V1 plus V2. Number four, total R is R1 plus R2. So you see there's a lot of formulas that we use, right? But the thing is we always use this first. If cannot solve, then we use these three. So we always, first thing, come to your mind straight away is V equals IR. Can we solve this? Can we solve that? And do take note, this V, I, and R, right, is depending on what you're looking for. If you're looking at V1, I need I1 and R1. If you're looking at total V, I need total I, total R. So you need to go and double check. Make sure that you label everything clearly and nicely. Okay? So first thing, 6 volts battery. All right? Now, what is the effective resistance of this circuit? So effective resistance means end circuit, right? This is total R. So they're asking you what's total R. So total R, first thing, if you want to find R, R is V over I, correct? Do you have total V? Yes, I have total V. Do I have current? No, no current. So the thing is, if you try to use R is V over I, total V, total R, total V, total I, we cannot use this. So we cannot use this one. Because why? We do have total I. We do have current. So going back, if we don't have current, we cannot use this to solve. So we go down, we check. All right, total R is R1 plus R2 plus R3 whatsoever. So we will write total R, or in this case, you have to follow a question, effective R. R1. So the thing is, we'll take our finger and we will trace. You have obstacle 1, R1, obstacle 2, R3, R2, and obstacle 3, R3. So you have 3 items. So R1 plus R2 plus R3. Okay, so all you need to do is just add them up. 6, 4, and 2. Now, because the app that I use to draw the circuit itself, it doesn't allow me to use decimal place. So by right, you should have 6.0, 4.0, 2.0. All of them are 2SF, so you just continue using the 2SF, 12 ohms. Okay. Then next, you want to find the current reading. So the thing is, you want to find I1. All right. So I1, problem is, do you have V1, R1? We do have, right? I2, do you have V2, R2? We do have I2, V2. Anything you have. So don't forget, this 6 is your total V. It's not V1, it's not V2, it's total V. Everything add up. Okay? So since V equals IR cannot help you solve for your I currents, let's look over here. Total I is I1 plus I. Is I1 equals I2, right? So first you write down that total I is I1 is I2. So the thing is, because we cannot find I1 and I2, which is A1 and A2, right? You will want to find total I. So total I, going back, can I use total V over total R? We can. Why? Because we have your 6 volts and we also just found your 12 ohms. So 0.50, and this is current A. So don't forget, because they're all the same, I1 and I2, they're all going to be 0.50 amperes. Okay, so with that, you have solved. So basically, you can see we always like kind of interchangeable. If this cannot solve, we use this. If this cannot solve, we use this. So it's more of a back and forth motion. So you need to memorize all of your formulas. So like I said, your electricity chapter, a lot of calculations, a lot of numbers, a lot of I1, V2, I2, whatsoever. So always very, very, very important. I need to emphasize this a lot. Please write your symbols properly and write whatever you are finding. Because if you don't write your symbols, you just throw in numbers, it will get very, very confusing. Okay, next one. You want to find potential difference across each resistor. So you want to find V1, V2, and V3. So first thing, V equals IR, right? So V1, I1, R1. Do you have V1? Yes, I have 0.50. Do you have R1? R1, let's say we use the 6 ohms, okay? So 6 ohms. So you end up with 3 volts. So this is V1. What about V2? I2, R2. Same thing, 0.50. What's I? R2, 4.0. 4.0, you end up with 2.0 volts. Same thing, V3. Now, even though there's no I3 in the diagram itself, we know that I3 will also be the same. Why? Because you're in a series circuit, current is exactly the same throughout. So because this going up, you have 2 ohms, 2.0, and 1.0 volts. So you have your 3 values over here. You have your 3 ohms, 2 ohms, 1 volts. And if you add them up, 3, 2, and 1, you add up to be 6. So your total V is 3 plus 2 plus 1. So all of them, you can still solve the same answer. Okay, so next part, next page, there's one more. So now you have 3 resistors connected to a 30-volt cell. So 30-volt cell, you have 3 resistors, do, re, mi, R1, R2, R3. So find the current, compare current for R1 and the one for R3. So because, compare, right? The current going through resistor R1, R3 are the same as the current at any point in a series circuit is the same. Okay, so because they are in series itself, they are arranged in series, they will actually have the same current itself flowing through them. Okay, so if they tell you current now is 1.5, so this is 1.5 amperes. So you can see if they don't give us the value itself, you want to throw in the values properly. So what is the potential difference across R1 and R2? So the thing is, it's across both of them. So they actually want you to find this. Okay, so you can find V1 plus V2, or you can basically, you want to find, there's multiple ways you want to solve it. So first thing, we know V equals IR, correct? So if you want to solve this, first thing, current is 1.5. R, now if you add R1 plus R2 together, it is possible as well. Okay, So if you solve R1 plus R2, what is R1? R1 is 5. What is R2? Is 10. So all you need to do is press the number. End up with 22.5. This is oops. Okay. Then if you want to play it safe, because everything is 2SF each, you can also use 2SF. Okay, but this is kind of unnecessary. Hence, so magic word hence means I need to use this part. Okay, hence I need to use V3. So hence means I need to use this value, right? So you can see 30 volts. So I can write total V is V1 plus V2 plus V3, right? So if I want to find V3, all I need to do is take 30 minus 22.5, that's 7.5 volts. Okay, and do take note, we only use this value, we don't use the round up value because this is inaccurate. So next, you want to find the resistance of R3. So you have to find R3, right? So R3, V3 over I3. So what's V3? Just found is 7.5. What's I3? We know it is a constant. It will be 1.5. So press the calculator. End up with 5.0. Now, because 2SF, we will keep it as 5.0 ohms. So this is the answer. Okay. So next, let's talk about your parallel circuits itself. Now, what is a parallel circuit? Basically, you must have components connected in 2 or more loops. So you can take your finger. So same thing, every time you want to ask yourself series or parallel, the first thing you want to do is always take your finger at your battery and you want to trace. And if you notice, if you trace, you have 1 loop here. And if you trace a second path, you have 2 loops here, right? So there's 2 different paths. And if I want you to take your notice to this point over here. So whenever you see these 2 dots, okay, there are hints that might be parallel. Because you only have these 2 dots when there's a split. Okay, so what I mean by split itself is you can see that your current is flowing like this normally, right? But at this point, because of these 2 dots, it will actually split. Okay, and once it split, you have 2 different current. You can see I2 and I3, they are 2 different values, and you will form back your current at the end. Now, if I'm going to color code it, so green is your total current. Okay, so anything that's touching the battery in series is total current. So all of these green color parts are total current. And next, I'm going to use yellow to tell you that this part is I2. And I'll use blue for the one below to tell you that this is I3. So the thing is, not all schools allow you to use highlighters itself, and sometimes you all mess up. It's a bit messy. So this one is just for visualization purposes itself. So what you can do is actually you zoom in here. Just remember, what goes in must come out. So all the current going in is equals to these 2. So how do you phrase this itself? Is total I is just I1 plus I2. Okay, so if I2 is 1 and I3 is 2, basically your I1 is going to be the sum of these 2, which is 1 plus 2. This is 3.0. Okay, now something special about your parallel is that your potential difference is the same across each. Now, do take note, it is each branch, not each component, each branch. Okay, so if this is your battery, this is V2, this is V3. Okay, so what happens is basically across the same parallel sides, you have the same voltage. Total V is equals to V1 equals to V2. Okay, so what I mean by this, remember when we were talking about your parallel, right? What happens is if I go 1 loop like this, I need to use up all of my 5 volts. So just to go through this one, I need to use up everything. So I need to use up 5 volts for this. Same thing, if I go my second path, I need to use up 5 volts for this as well. So both of these are 5 volts each. So as long as you know that this is parallel, this whole thing will be 5 volts. Now, why do I need to emphasize about each branch? Because sometimes you have this kind of circuits. So what I mean by this is that this entire stretch is the same as the one on top. So if this guy is 10 volts, the whole yellow is 10 volts. And if these two are the same, this will be 5 volts, 5 volts. If and only if they have the same resistance, then you can split nicely in two. If they are not the same resistance, just need to know that they add up to be 10 volts. Okay, just a random number itself, but do take note that for this is 10 volts. Okay, so I say it's across the entire branch, it is the same, not for each component. I want you all to take note of that. Okay, for the whole branch. Now, this one is a little bit more confusing itself. Is basically if you want to find effective resistance, we use this formula. Okay, we don't use the one on top, but the one on top is the official correct way of solving it. So, for example, you have a standard parallel circuit. You have one R1 and one R2. If you want to find the effective, which is your total resistance, just throw in the numbers. Now, each fraction represents each branch. So you have two branch, right? Branch 1, branch 2, 1 and 2, right? So you have two fractions. So you have half and 1/3. So half plus 1/3, you will get 5 over 6. 1 over 5 over 6, you get 1.2. Okay, so because of this, you need to be careful, especially when you're dealing with effective resistance. It's a little bit more tricky than your series circuits. So over here, just now, same as what we did, whenever you see a parallel, first thing you want to do is, number one, V equals to IR. That's why I told you that this formula, V equals IR, R is V over I is V over R, is your most important one, okay? Then number 2, number 3, and so forth. I'm going to shift it slightly to the side so that we have space to show you, okay? So number 1 is total I is I1 plus I2, okay? Number 3, total V is V1 and V2. They are the same. Number 4, your effective resistance or your total resistance. Okay, is this weird formula R1, R2. I want to bracket it. Okay, so first thing, let's talk about this. You have a 3-volt cell, so do be careful. So if each current, do, re, mi, is all 3 volts, 3 amperes each, what's the resistance of each resistor? So you want to find R. V1 over I1. V1 is 3. Why? Because they are parallel across each branch, your potential difference is the same. All of them will be 3, and all of them will have this. So R1, R2, and R3, they all have the same value, 0.30 ohms. Okay, because the values they use are exactly the same. V2 over I2 is the same as V1 over I1, same for 3 as well. Okay, hence magic word, I need to use this. Find the effective resistance circuit. So you have to find total R. So total R, right? We need to use R1, R2, and R3. So 1 over 0.30, 1 over 0.30, 1 over 0.30. And now it's 0.10 amperes. Oh, sorry, ohms. Okay. Wait, I might have calculated some things wrongly. Yep, I calculated things wrongly. Okay, I made a mistake on top. 3 divided by 1 is 3. 3.0. Okay, so this should be also 3.0. So I messed up. So as you can see, it's very, very easy to get confused because there's so many numbers itself. So you need to be very, very careful itself. Okay, so over here, you should end up with 9 ohms. All right, so you have 9 ohms over here. So this is your effective resistance. No, sorry, not 9 ohms. Same thing. See, mental sum doesn't work. Press your calculators, please. Okay, you should have 1.0 ohms. Yes, you should have 1.0 ohms. All good. Then next, you are given 2 identical 10 ohms resistors. So take note, identical. So you are now parallel to battery, and they tell you V, right? And your current is IP. Sketch the circuit. So parallel, first thing, you have a battery. So battery I'll draw like this. It is a voltage of V. You have two resistors that are 10 ohms each. And the current flowing through them is IP. Okay? IP. Same thing, you have 10 ohms over here as well. Close it. Just like that. All right? The next, if I connect it in series to the same battery, and you now have this current itself. So now same battery, B, but now I have your two resistors in series, and now your current is IS. Okay? So determine the ratio of IP and IS. So basically we need to calculate what's IP and what's IS. So for IP, you notice this is actually your I1. Okay? So IP, I need to use V over R. Okay? And this is your V over 10. So you get 0.10 amperes. Okay? Because we express it in terms of V itself. All right, then next for your IS itself, IS is a bit different because IS, if you notice, it is using your total current. Because we don't have V1, we don't have V2, right? We only have total V. So we take V over your total R, right? It's V over 10 plus 10. Okay, so V over 10 plus 10 should end up with 0.05. 0V amperes. Now, so all we need to do now is just put the ratio, right? And your ratio is IP to IS, which is IP on top to IS. So 0.10V, 0.050V itself. Do this, you end up with 2. So basically the current flowing through your IP is 2 times that of your current flowing through this. You understand? So ratio, because it's amperes over amperes, there's no units for this. Now, if you remember, just now we did one question where you had a series in a parallel, right? So sometimes it is a little bit confusing. So for example, basically, if you're in series, you can combine it like this. If you have 2 parallel, you can combine it like this as well. Just use your resistance formulas respectively. So what I mean by this is, if you take a look at this, the one on the left, top left. First thing, if you take your finger and you try to trace, you'll notice that, hey, I have one over here. And if you take a second path, you'll notice that, hey, I have a parallel, but this guy is overlapped twice. So what's the problem? Problem is, if you draw this to the dot over here, all of these are total current. All of these are current 1. This is current 2, right? So now you have a series and a parallel. So to avoid the confusion, it's basically you see this yellow and this blue color part. If you simplify it using your effective resistance formula, 1 over 1 over 2 plus 1 over 2, you end up with 1. So basically, if you are finding current, you need to solve it. You need to simplify it and solve it. Okay? If you want to find total current, you need total V, total R. You have total V, but you need to find total R. So it's 2 plus 1 over 2 plus 1 over 2. Okay, so let me just solve it to you. If you want to find effective resistance, first thing you have your 2 ohms, which is this guy, and you have this parallel, which is 1 over 2, 1 over 2. So the whole thing, so you actually end up with 3 ohms. So the whole entire setup here is 3 ohms. Okay, this is 3 ohms. On the other hand, if you look at this, you have total, you have your this one, you have this one. So do take note. Basically, you can combine the two inside to just form this, and then you can just solve I1, I2 respectively. Very straightforward. Okay. So just be careful of the values. This guy can be 2.5 volts, 2.5 volts. Because it's equal resistance, you can just divide by 2 like this. But then for this guy, this is 5 volts. Okay, so voltage, resistance, and current, they are not always the same in separate branches or in your series or parallel. Do double check whether it's series in parallel, parallel in series, or whatsoever. Okay, So let's take a look. Now, first thing first, from your battery to this point, this is total current. Okay, then you have current 1, you have current number 2. Straight away, this is a complex circuit, series and parallel together. So now the question asking you, what's the direction of current flow in the circuit? They never say electrons, so I'm going to assume it will be conventional current flow. Okay, so direction of the current will be in this direction. All right. So what is the effective resistance of this circuit? So first thing is you look at the yellow color part. These two are series. Okay, so if you combine these two, they are basically be 4,000. And this one over here is 3,000. Right? So if you want to find your effective resistance itself, you can do now because I have 2 branches, 1 and 2, yellow and blue, right? I should only have 2 fractions. And because I have the 2,000, which is in series, I'll just add them up, don't get 2 brackets. And you have 1,000 plus 2,000 over here, close the bracket, press your calculator. You should, if I'm not wrong, get a fairly weird number. Yes, you do end up with a long number, long decimal itself, 1714.3. So you simplify it, okay? We'll just use 2SF or 3SF accordingly. So we use 2 because of the 12 volts here. So we just use 2SF, 1700, and this is resistance, so 2SF. Okay, so do take note, we should still write the 5SF version because we might need to use it later on. So what's the current flowing through your battery? So keyword current, battery. So they're asking you for total I. So if you want total I, first thing is V equals IR formula, right? Total I, total V, total R. So ask yourself, what's total V? Total V is 12. Correct? 12. What's total I? Total R. Total R is 1714.3. So you take your value, 12 divided by 1714.3, you end up with a very, very small value, 0.0699999. You just round it up, 0.070. Current 2SF. Okay, so to take note about this, let me just double check if the values are correct. Yes. So next, what's the current flowing through P? Compare the current flowing through P and compare the current flowing through Q. Explain your answer. So you basically want to compare this current, the yellow current versus the blue current, right? So if you don't want to do calculation itself, just need to remember what is I. I is V over R, right? Okay. So you can see across point P and Q, the potential difference, both branches are the same. Okay, they are the same. Why? Because they are parallel. Okay, I'm just gonna shift this one over. So since they are parallel, they have the same PD. Okay, so you can see when I try to explain, I'll try my best to always say current, voltage, and resistance. Okay, since, okay, or don't use since because it's repeating, as the resistance in the branch containing point P is greater or larger than that containing point Q, or than the branch containing point Q, the current flowing through point P is smaller than through point Q. That's all. So you can see over here, you talk about your potential difference, and you talk about them being the same because you are parallel. And then what happens? Resistance is greater, then your current is smaller. So you can see all of the keywords over here because this is a comparison question. So ultimately, you need to talk about I, V, and R, and whether it's greater than, less than, or whatsoever. What's the relationship? So you can see over here, try to always write all your keywords, I, V, and R. Make sure you have all of them. Talk about V and R first before you conclude about your current I. Okay, so there's more. So you see A1, 2, A3, V1, V2, V3, there's a lot of them, right? So first thing is, let's try to always solve the easiest one first. So before we start solving, ask yourself, series or parallel? So you just take a finger. You have one, you have two parts. Obviously, this is going to be a series and a parallel because this guy overlaps. So taking your highlighter, before and after every branch. You have this one, you have branch number 1, you have branch number 2. Okay, so this is your very weird circuit. So first thing is, let's try to solve the easiest one that we can try to solve, which is your current. So let's find total current first, okay? So if you want to find total current, which is A1 and A2, sorry, A1 and A3, okay? These guys are your total I. Okay, because they are the green part. So if I need that, I need total V, I need total R. Okay, so if you notice, we need total R first, right? So before we actually solve this, you can actually solve for total R first. What is total R? You have 3, 3.0 plus, because these two guys are parallel, so 1.60, and this is 3.0. So you press this, fraction it if you need to. So 3 plus 1 over 6 plus 1 over 3, we end up with 5. So this is 5 ohms. Okay, so if this is 5 ohms, I just need to throw in my numbers. Do we have total V? Yes, we do. It's 6. So it's 6 divided by 5. We end up 1.2 current amperes. Okay, so we solve for A1 and A3 already. Okay, so we just go down the list. So now you see V1 here. So let's ask ourselves, do we have V1? We need I1, we need R1. So you look at I1. I1 is actually your total current. So we have 1.2. Do you have resistance? We do. We have 3.0. Okay, so this is 3.6 volts. So we solve for V1 already. Okay. Now V2 and V3, these two guys are parallel to each other, which means V2 and V3, they're actually the same. Okay, V2 and V3, they're actually the same. So if you think about it, total V is 6. V1 plus the parallel will give me 6. So I'll just need to take total V minus V1, which is 6 minus 3.6, 2.4 volts. I have solved for V2 and V3. Okay, so if this is confusing to you, let me simplify it. Basically, you have 6 volts, 3.6 volts, and these two guys, they are 2.4 volts. So V2 and V3, they are the same. Okay, can you see that? Basically, a simplified version of the drawing, it looks like this. So now we have A1, A. So now we have solved V1, we solved V2, V3, we are left with just A2. Now A2 itself, right, is actually I2. So if I want I2, I need V2 and R2. So do I have V2? Yes, I do. Do you have R2? What's R2? Look up. R2 is 3 ohms. So 3.0. So 2.4 divided by this, if I'm not wrong, you should get this value. Okay, let me just double check. 2.4 divided by 3, 0.80. Yes. So you have solved all of your components. So they don't need to always be in a certain order itself. Just solve the easiest one. Usually your easiest is usually your total V, total I, total R. Solve that first, and then you just solve the series. Parallel, we always leave it to the rest. So you can see, do it step by step, bit by bit. Don't rush everything in one diagram or one equation. You'll make a mess. And please, always label carefully which is which. If you just keep using numbers and you don't write units, which I know a lot of you don't do that. If you just write numbers, you get very, very confusing. You can see there's so many V1, V2, I1, I2, I3, all sorts of symbols there are. If you don't label them, it gets even more confusing for you and for the marker. So if the marker don't understand what you're doing, they're just minus one big fat 0. Okay,